Assalamualaikum and hi everyone. Jadi sesi kali ini kita akan lihat presentation para pelajar yang akan berkongsi ilmu bersama kawan-kawan bagi persediaan menghadapi final exam yang bakal tiba dalam sesi Dari Kita Untuk Kita. Jom kita tengok.
Assalamualaikum and hello everyone. So today we are going to learn about chapter 13, which is gas laws and kinetic theory. So today we're gonna learn 13.1, which is ideal gas equations. So the first learning outcome is solve problems related to ideal gas equation, which is PV equals to nRT. So the next learning outcome is discuss the following graph of an ideal gas, which we have PV graph at constant temperature, VT graph at constant pressure, and PT graph at constant volume. So next, what is ideal gas? An ideal gas is defined as a perfect gas which obeys the three gas laws, which is Boyle's laws, Charles' laws, and Gay-Lussac laws exactly. So 1 mole of gas at standard temperature and pressure STP, which is T equals to 273.15 Kelvin, pressure at 101.3 kilopascal, and volume of 1 mole of gas, which is 0.0224 meter cube. So from the equation PV equals to nRT, kita boleh dapat R constant by substituting the value, which is PV over T. So kita substitute by the value that we have here, kita akan dapat 8.31 joule per Kelvin mole. So right here, like this. So what is R in PV equals to nRT? R is called Molar Gas Constant. It is constant and its value is the same for all gases. Thus, PV over T equals to R. So PV equals to RT. Kita pindahkan T ni bawa sini. Where Vm is volume of 1 mole of gas. So next is, for n mole of an ideal gas, the equation of state is written that PV equals to nRT, where n is the number of mole of gas. So there are two equations that we can use for calculate the value of number of moles. The first one is n equals to m, which is mass of a gas, over m, which is molar of gas. Right here. Okay. So the next equation, we can also calculate the number of moles by using the equation n equals to n, which is number of molecules, over Na, which is Avogadro's constant. So how we can get this equation? First, we write the main equation. PV equals to nRT, where the value of n, we can substitute this equation. So PV equals to n over Na RT. Now kita pindahkan dia Na and T. Now we know that R over Na is constant, so we just substitute K and T. Now we get the same value just like this. Okay, next one is graph for an ideal gas. So PV graph at constant temperature, which is Boyle's law. Boyle's law states that the pressure of a fixed mass of gas at constant temperature is inversely proportional to its volume. So, if temperature T is constant, pressure is inversely proportional to its volume. This one. So, just try, kita tulis equation PV equals to nRT. So, we know that temperature is constant. So, temperature is constant. So, this is constant. Everything here is constant. So, we can write that PV equals to constant. So, we can write it like this. P equals to constant over V. So, by doing like this, we know that P is inversely proportional with volume. Sama kan? Okay. Now, from ideal gas equation, PV equals to nRT. Therefore, we know that PV is constant. Yep, just like I do that. Or can be write as P initial times V volume initial equals to P final times V final. Right here. So how we want to know that is Boyle's law? So from this graph, we know that if the volume is decreasing, so we know that if the pressure is increased, so the volume will decrease. Macam ni, bila kita tambah pressure, kita tolak dengan pressure, so the volume akan berkurang. So the molecule dalam tu akan bergerak lagi laju lah. So boleh tengoklah dia punya kat sini. So kat sini, this is for this one. So if the volume is increased, then the P will decrease. So this is Boyle's law. So from here pun, we can see that nRT is constant. So next is the graph of the Boyle's law. So the number one is the pressure against volume graph at different temperatures. So the curve in the graph represent different temperatures. So ada dua temperature lah sini, ada T1 and T2. Each curve in the graph above is at constant temperature. So T is constant. And such curves are isothermal. So kita belajar dalam chapter 14, this one is isothermal too. So based on the graph, when the temperature is constant, pressure decrease when volume is increased. So sekarang kita nak tahu tu betul kan? So we made a point here. We make point here A, point B. So kita tarik sini, we make a line. So let's say that this is VA and this is VB. Then this is PA and this is PB. So from here we know that TA equals to TB. Temperature A equals to TB, right? Because the temperature is constant. But we can see here that VA is bigger than VB, right? And also PA is smaller than PB because it is inversely proportional. So we know that from this graph that P is inversely proportional with volume. So the second one is if the graph is pressure times volume against pressure graph at different temperatures. So this is all the graph of the Boyle's law. And the third one is also pressure against 1 over V graph at different temperatures. And also the fourth graph is about pressure times volume against volume graph at different temperatures. So next is graph for an ideal gas. VT graph at constant pressure, which is Charles' law. So constant pressure, we know that Charles' law. Charles' law states that the volume of a fixed mass of gas at constant pressure is directly proportional to its absolute temperature. So from ideal gas equation, PV equals to nRT, when pressure P is constant, volume V is directly proportional to temperature. So we can write, kita boleh tulis the equation PV equals to nRT. So dia ada cakap the P is constant. So we need to collect all the constant value here. Put kat sini. And T is not constant, right? Temperature is changing. So we move it to here. So we know that V over T is equals to nR over P. So all of this is constant. And we will write it V over T equals to constant. So we know that V equals to constant times T. So that means that V is directly proportional with T. So ada kat sini juga lah, dia ada tulis where nR over P is constant. Therefore V is proportional with T. It also can rewrite as V over T equals to constant. Yeah, right here. Or this one, V initial over T initial equals to V final over T final. Okay, this one is also Charles' law. So let's look at the graph of the Charles' law. Since V is proportional with T, since V is directly proportional with T, the graph of the Charles' law can be represented as below. So from this graph, we know that if V is increased, the T will also increase at constant temperature. So bila P constant, V will increase and T also increase. So the graph will be like this. Yeah. So for PT graph at constant volume, Gay-Lussac's pressure law, we know that the volume is constant. So Gay-Lussac's law states that the pressure of a fixed mass of gas at constant volume is directly proportional to its absolute temperature. From ideal gas equation, PV equals to nRT, when volume V is constant, pressure P is directly proportional to temperature. Jadi kita tulis the equation PV equals to nRT. Kita kumpulkan, collect all the constant value. So we know that volume is constant, so volume will go here, but the temperature is changing, so it will go here. So P over T equals to nR over V. So same like here, nRV is constant. So we will get this like equation like this, PT equals to constant, like here. Or we can rewrite the equation like this too. P initial over T initial equals to P final over T final. So let's look at the graph of the Gay-Lussac's law. Since P is directly proportional with T, the graph of the Gay-Lussac's law can be represented as below. So let's look at the graph of the P. So since P is increased, then T will also increase too. So kita tahu P over T is constant. So we know that P equals to constant times by T. So we can get that P is directly proportional with T. So the graph is true after all. So let's look at this simulation. So let's go to the examples given. So number one is the pressure of a sample of gas in 5 atm in a 1.2 liter sealed flexible container. If the pressure gets raised to 8 atm at a constant temperature, so we know if it is constant temperature, we know that is Bohr's law. So what is the new volume? Okay, so we need to find the V2. So given that V1 here, the V initial here is 1.2 liter. So this is pressure initial. So this is pressure final. So from Bohr's law, we can write the equation like this. P initial times V initial equals to P final times V final. Since P can be in atmospheres and V can be in liters, so we don't have to convert any units. Instead, we just rearrange the equation to solve the V final and plug in all the numbers. So, to find V final, we just rearrange the equation P1 over P2. So now, we just substitute all the values. Then we will get 0.75 liter. So the new volume is V equals to 0.75 liters. Okay, next one is at 40 degrees Celsius, the volume of a gas is 300 milliliters. So from here, 40 is T. But we need to convert to Kelvin first. So we need to add 273.15 Kelvin. So this being 300 milliliter, this is volume. So we take it as V initial. The temperature of the gas get raised. So it get raised to 55 degrees Celsius. We need to change it to Kelvin first with no change in pressure. No change in pressure. That means that pressure is constant. So since pressure is constant, we know that this is Charles' law. So what is the new volume of the gas? So we need to find the V final. This is T final. This is T initial. V initial over T initial equals to V final over T final. So we are given all but the new volume, which is V final. So to find the new volume, we rearrange the equation, which is V final equals to V initial over T initial times T final. So we can change the volume, we can convert the volume, which is in milliliter, to liter. So we can substitute the value 0.30 liter over 301.3.5 times 328.15. So we will get in liter 0.314. So we can also change the value in milliliter, which we will get 314.0 milliliter. So that is the answer for the new volume of the gas. So next is this question. So refer to figure. Initially A contains the volume is 3 meter cube of an ideal gas. At a temperature T equals to 250 Kelvin and a pressure P equals to 5 times 10 power of 4 Pascal. So while B contains, so the volume is 7.2 meter cube of the same gas at the temperature equals to 400 Kelvin, and the pressure is P equals to 2 times 10 power of 4 Pascal. So calculate the pressure after the connecting tap that has been opened and the system reached equilibrium, assuming that A is kept at 250 Kelvin and B is kept at 400 Kelvin. So we know that when the has opened and the system reached equilibrium, we will know that the pressure will be the same. So that means that PA equals to PB. We will get P. That is the pressure after the connecting tap has been opened, the system reached equilibrium. So we know that all the value is changing, right? So we will use this equation. P naught times V naught over T naught is equals to P final times V final over T final. So we know that there's two PVT, which is A and B. So we can write that P initial A times V naught A over T naught A plus P naught B times V naught B over T naught B. So there's 2, and then the second one is P final A times V final A over T final A plus P final B times V final B over T final B. Now that the pressure after the connecting tap has been opened is reached equilibrium, which is PA equals to PB equals to P. So we can factorize the value. So it will be P times V final A over T final A plus V final B over T final B. This one is PA V naught A over T naught A. So we just substitute the value. 5 times 10 power of 4 times V equals 3 over T is 250 plus times 2 times 10 power of 4 times 7.2 over 400 is equals to P V3 over 250 7.2 0 over 400. Then P we will get 3.20 times 10 power of 4 Pascal. So that is all from me. Thank you.
Good morning to Madam and my friends. I am Tiawani from S15B12. Today I am going to sum up the subtopic, chapter 13.2, Assumptions of Kinetic Theory of Gas. Before we learn about the assumptions of kinetic theory of gases, we must know that what is the kinetic theory of gases. To study the action of gas molecules, we must use a theoretical model, and this model is known as kinetic theory of gases. So there are 7 postulates for kinetic theory of gases. All gases are made up of identical atoms or molecules. All atoms or molecules move randomly and haphazardly. The volume of the atoms or molecules is negligible when compared with the volume occupied by the gas. The intermolecular forces are negligible except during collisions. Interatomic or molecular collisions are elastic. The duration of a collision is negligible compared with the time spent traveling between collisions. Atoms and molecules move with constant speed between collisions. Gravity has no effect on molecular motions. So we have to remember the 7 assumptions of kinetic theory of gases in our syllabus. I sum up all the 7 assumptions of kinetic theory of gases using rave method. So what is rave? R stands for random motions. So all gases and particles are moving in random motion. And A stands for attraction, none between particles. So the intermolecular forces is negligible, except during collisions. And V stands for volume. Molecules or particles have negligible volume compared to volume of gas. So the volume occupied by the gas is much more bigger than the volume of atoms or molecules. And E is elastic collisions. So intermolecular or molecular collisions are elastic. And also D, the last one, duration of collision is very short compared to time between. So the duration of a collision is negligible compared with the time spent traveling between collisions. So these are the 5 main assumptions that you can memorize it easier for you all. So that's all from me. Thank you very much.
Guys, in today's video we're going to learn about root mean square speed, which also known as VRMS. Okay, first of all, what is meant by root mean square speed? Okay, let's say I give an example. In a container got a lot of gas particles. Okay, the important notes is every gas particle in a molecule move in different direction and different speed. Let's say this V1 move in different direction, different speed, V2 move in different direction, different speed, V3 move in different direction, different speed, and so on. And the last molecule we call as Vn. Okay, what's mean by root mean square speed? Since in a molecule, every gas particle move in different direction and different speed, so we must use root mean square speed to find the average velocity for each of gas molecule in a gas. Okay, how do we find? Okay, I show you back the screen. Okay, this is, since I put a arrow here, this indicate the way to find the root mean square speed. Okay, first of all, what should we do? Since the arrow is going this side, first of all we must square. We must square it. Later, mean. Then the last part is square root it. So this is known as root mean square speed. How do we write it? Is VRMS square plus V1 square plus V2 square plus V3 square plus so on, and the last molecule Vn square divided by the total number, and then we square root it. Then we will get the VRMS of the particular molecule. Other than this, we got other 2 formula, which are VRMS equals to square root 3kT over m, and the other one is VRMS equals to square root 3RT over mr. Okay, let us look at this. K, what is K? What's the value for K? The value for K is 1.38 times 10 to the power of 23. Since the K is constant, so we just substitute this value into the formula. Okay, temperature. Don't forget in this chapter the unit for temperature must be in Kelvin, not in degrees Celsius. So whenever the question gives you in degrees Celsius, don't forget to convert it to Kelvin. Okay, mass. Okay, since if the question gives you mass of one molecule, then we must use this formula. Then how about this formula? This formula is when the question gives you molar mass, then you use this formula. Okay, let us refer to some questions. Okay, question 1. The RMS speed of hydrogen molecule at a particular temperature is 1330. What is the RMS speed of nitrogen, this is nitrogen molecule at the same temperature? And the molar mass of, given the molar mass of hydrogen is 2.0 gram per mole and molar mass of nitrogen is 28 gram per mole. Okay, let's extract some information from the question given. What already given? Given temperature. Given the RMS of hydrogen molecule is 1330. Okay, let us assume that hydrogen as 1. So we put VRMS1, which indicate hydrogen molecule. So VRMS1 equals to 1330. Okay. Other than that, what information they got? Molar mass of hydrogen. Okay, they already give us molar mass of hydrogen. Since 1 is indicate hydrogen, so molar mass of hydrogen is 2.0. And don't forget to convert gram per mole into kg per mole. Other than that is molar mass of nitrogen. Okay, 2 is indicating nitrogen. Okay, what's the molar mass of nitrogen is 28. Okay, and again don't forget to convert it to kg per mole. Other than this, the most important information in this question is the both molecule is at the same temperature. What is meant by same temperature? Same temperature means the temperature of hydrogen molecule equals to temperature of nitrogen molecules. So it is T1 equals to T2. Okay, first of all we must find T1 first. Why we must find T1 first? Because if we want to find the VRMS, without the value of temperature we can't find the VRMS of nitrogen molecule. So first of all we must find the temperature. Okay, as usual use this formula, VRMS1 equals to square root 3RT over MR. Why we use this formula? Since the question already give molar mass, so just use this formula. And as usual substitute, then we get T1. The value for T1 is 141.91 Kelvin. Don't forget the unit must be in Kelvin. Okay, since we already got the value for temperature, in this question what does that? Same temperature. Same temperature means T1 must be in T2. So just substitute the value of T1 equals to T2, and as usual use the formula. Then we got the final answer, which is the RMS of nitrogen molecule. Into the second question. Calculate the temperature of carbon dioxide given the molecular mass is 44 gram produced in a fire if the root mean square velocity of the gas is 475. Okay, what is given? Given the molecular mass of carbon dioxide. Extract the information. Okay, given the molecular mass of carbon dioxide is 44 gram. And again don't forget to convert the gram into kg. Okay, and the other information is given the root mean square of the gas. Okay, they already give us the VRMS of the carbon dioxide. Then what the question asks us to find is the temperature. Okay, as usual use the formula VRMS equals to square root 3RT over MR. Okay, again since the question already given the molecular mass, then use this formula and substitute all the value into the formula. Then we get the temperature of carbon dioxide. Okay, let us refer to the third question. The molar mass of oxygen is 23 gram per mole at 300 Kelvin. Calculate the root mean square speed of the oxygen molecule. Again extract the information given. What's given? Molar mass of oxygen. Okay, extract molar mass of oxygen is 23 gram per mole. Don't forget to convert it to kg per mole. And then what else is given? Given the temperature. Temperature is 300 Kelvin. Since the question already gives us the value of temperature in Kelvin, so we no need to do anything. Okay, again the formula VRMS equals to square root 3RT over MR. Why MR? Because already given molar mass. Okay, substitute all the value into it, then we got the root mean square speed of oxygen molecule. Let's refer to the last question. a balloon is filled with helium at 25 degrees Celsius. Look at this. It's filled with 25 degrees Celsius. What I told before, the unit for Kelvin, the unit for temperature must be in Kelvin. So what we must do? Extract the information and then change the unit of degrees Celsius into Kelvin. How should we change? We must plus with 273.15. Okay, then we got the temperature in Kelvin. Other than that, we got the mass of helium atom is 6.65 times 10 to the power of negative 27. Okay, they already give the mass of helium atom. Extract it out and then calculate the root mean square of the helium atom. Okay, they ask us to calculate the root mean square of helium atom. Since in this question is different, since it already give us mass, so change the formula bit. The formula will be square root of 3 kT over m. Then as usual, and don't forget to change the constant value, since for molar mass it will be R. If mass, the constant will K. So as usual, substitute, then we got the answer for root mean square of helium atom. That's all for today's video. I hope this video will help you a lot. Thank you so much. Bye.
Assalamualaikum and hi everyone. My name is Norazlina and today I will explain how to solve problems related to equation P equals to 1 over 3 and mvrms squared and P equals to 1 over 3 density vrms squared. Question number 1. When the pressure of an ideal gas is increased from 5.5 multiplied with 10 power of 4 Pascal to 1.5 multiplied with 10 power of 5 Pascal, its volume decreased from 2.5 multiplied with 10 power of negative 3 meter cube to 0.5 multiplied with 10 power of negative 3 meter cube. If the initial root mean square RMS velocity of the gas is V, determine the final RMS velocity of the gas in terms of V. Mula-mula kita keluarkan nilai yang kita dapat daripada soalan, iaitu P1 sama dengan 5.5 darab 10 kuasa 4 Pascal, P2 sama dengan 1.5 darab 10 kuasa 5 Pascal, V1 sama dengan 2.5 darab 10 kuasa negatif 3 meter cube, dan V2 sama dengan 0.5 darab 10 kuasa negatif 3 meter cube. V1 kuasa 2 maksud dia ialah mean square speed, manakala punca kuasa V1 kuasa 2 sama dengan root mean square speed, ataupun yang ni kita panggil dia VRMS1. VRMS1 sama dengan V, jadi kita nak cari nilai untuk VRMS2 kan, kita guna nilai PV sama dengan 1/3 nm V square. Lepas tu kita buat macam ni, square root dua bahagian ni, dia akan jadi square root P1 V1 over square root P2 V2 sama dengan punca kuasa 1/3 nm V1 kuasa 2 per punca kuasa 1/3 nm V2 kuasa 2. Memandangkan 1/3 nm ni constant, kita potong saja. Lepas tu dia akan dapat macam ni. Punca kuasa V1 kuasa 2 per punca kuasa V2 kuasa 2. Kemudian dia akan dapat macam ni kan. Yang sebelah pun kita tukar. Dia akan jadi punca kuasa P1 V1 per V2, V2. Punca kuasa V1 kuasa 2 ni, dia akan jadi VRMS1. Kita tengok dari sinilah. Manakala punca kuasa V2 kuasa 2, dia akan jadi VRMS2. So, kita gantikan, kita akan dapat punca kuasa V1 V1 per V2 V2 sama dengan VRMS1 VRMS1 per VRMS2. Memandangkan soalan dia nak VRMS2, kita susun balik dan akan dapat punca kuasa V2 V2 per V1 V1 darab VRMS1. Masukkan nilai yang kita dapat ni ke dalam ni. Kemudian darab kalkulat macam biasa dan kita akan dapat 0.739V. Question number 2. Calculate the RMS speed of air molecules in a container in which the pressure is 1.0 multiplied with 10 power of 5 Pascal and the density of air is 1.3 kg m power of negative 3. Mula-mula kita keluarkan nilai yang kita berdapat daripada soalan, iaitu kita akan dapat P sama dengan 1.0 darab 10 kuasa 5 Pascal MP and density sama dengan 1.3 kg m power of negative 3. Kita guna equation P sama dengan 1/3 density VRMS square. VRMS square sama dengan 3P over density. Kita dah susun balik kan, dia akan dapat 3P over density. Square root kan dua-dua belah akan jadi VRMS sama dengan square root 3P over density. Kemudian kita masukkan balik nilai dia ke dalam sini. Masukkan balik nilai. Dan akhir sekali VRMS sama dengan 480.38 ms power of negative 1. Question number 3. The RMS speed of helium at STP is 1.30 km s power of negative 1. Calculate the density of helium at STP. Okey, mula kita keluarkan nilai yang kita boleh dapat daripada soalan. Kita akan dapat pressure at STP in Pascal is 1.01 multiplied with 10 power of 5 and VRMS sama dengan 1.30 km s power of negative 1. So, P sama dengan 1/3 density VRMS square. Kita guna equation ni dan susun balik, dia akan dapat density sama dengan 3P over VRMS square. Masukkan nilai yang kita dah dapat ke dalam ni. So, the final answer we will get density equals to 0.179 kg m power of negative 3. That's all from me. Thank you.